At this point, I would like to introduce the unifying framework behind everything we have discussed so far, Digital Healthcare Engineering, or DHE. DHE represents a fundamental shift in engineering philosophy. Within this framework, ships are no longer viewed as static assets or disposable products. Instead, they are treated as patients. Correspondingly, engineering is no longer confined to design, inspection, and repair. It becomes healthcare. Healthcare implies continuous care across the entire life cycle. It is based on real-time monitoring, early diagnosis, predictive assessment, and timely intervention, long before failure occurs. Just as in human healthcare, the objective is not to wait for collapse, but to preserve health, functionality, and resilience over time. Digital healthcare engineering integrates real-time sensing, living digital twins, secure data transmission, and AI-driven intelligence into a single, coherent lifecycle framework. It enables ships to be designed, operated, monitored, and cared for as living systems, adapting continuously to aging, uncertainty, and changing operational demands. In the next slides, I will show how DHE transforms this philosophy into a practical and implementable engineering reality, reshaping safety, sustainability, and resilience for the next century of maritime systems. Healthcare for engineering structures and machinery systems is closely analogous to healthcare for human beings. When we use the term healthcare in an engineering context, we are not speaking metaphorically. Rather, we are redefining the scope of engineering responsibility. In this sense, healthcare means the continuous preservation of system health, rather than episodic inspection and repair after damage has already occurred. For ships, this concept of healthcare encompasses four inseparable dimensions. First, structural integrity, the continuous monitoring of stresses, fatigue accumulation, corrosion, damage initiation, and damage evolution. Second, machinery condition, understanding performance degradation, efficiency loss, wear, and the development of faults over time. Third, environmental exposure, capturing the real operational loads imposed by waves, wind, temperature, and increasingly severe climate extremes. Fourth, human well-being, recognizing that fatigue, cognitive load, and working conditions directly influence safety, decision-making, and overall system performance. These dimensions cannot be managed in isolation. Harsh environmental conditions accelerate structural degradation. Degraded machinery increases human workload, and human fatigue, in turn, raises the likelihood of operational error and accidents. True engineering healthcare is therefore preventive and holistic. It shifts the role of engineering from fixing failures to maintaining health, continuously, intelligently, and across the entire socio-technical system. Digital healthcare engineering is not a single technology. It is a structured, life cycle framework built upon 5 tightly integrated modules, each essential to the integrity of the whole system. The first module is real-time multimodal sensing. This provides continuous data streams from structures, machinery, the operating environment, and human operators forming the nervous system of the ship. The second module is secure data transmission. This ensures that sensed information is reliably, continuously, and securely transferred between ship and shore with data integrity, traceability, and trust preserved. The third module is digital twin simulation. Here, physics-based models are continuously updated with real-time data to represent the true evolving state of the ship, rather than an idealized design condition. The fourth module is AI-enhanced diagnostics. AI interprets digital twin outputs to detect anomalies, identify root causes, and assess emerging and future risks under uncertainty. The fifth module is predictive health management. This module transforms diagnosis into actionable decisions, optimizing maintenance strategies, operational planning, and long-term lifecycle management. These 5 modules do not operate independently. They function as a single, coherent healthcare system. Remove any one module, and the effectiveness of the entire framework collapses. Together, they enable continuous, intelligent, lifecycle care of ships as living engineering systems. One of the most powerful features of digital healthcare engineering is that it spans the entire life cycle of a ship, from the earliest concept design to final decommissioning. DHE is not an add-on applied after delivery, it is embedded from the very beginning. At the concept and preliminary design stage, digital twins are used to explore safety margins, energy system choices, structural robustness, and long-term performance under uncertainty. Design decisions are informed not only by compliance, but by predicted lifecycle health. During construction, real-time sensor data and digital models are used to ensure that the ship being built faithfully matches the ship that was designed, reducing hidden defects and ensuring traceability from yard to operation. Once the ship enters service, the digital twin becomes a living companion. continuously updated to reflect real operational loads, environmental exposure, degradation, and usage patterns. This enables informed, evidence-based decisions on maintenance, operation, and risk management. As the ship ages, DHE supports safe and economical life extension by quantifying remaining useful life and evolving safety margins, rather than relying on conservative assumptions or calendar-based rules. Finally, at decommissioning, accurate digital records support safe dismantling, waste management, and environmental responsibility, closing the life cycle loop. In this way, DHE transforms ship engineering into a true cradle-to-grave discipline, grounded in continuous knowledge and healthcare, rather than periodic inspection and fragmented snapshots. Let me now illustrate how digital healthcare engineering operates in practice, beginning with structural healthcare. Traditionally, structural integrity has been assessed through periodic inspections, simplified calculations, and conservative design assumptions. DHE replaces this episodic approach with continuous quantitative health assessment. In a DHE framework, real-time sensors continuously measure structural stresses, motions, fatigue accumulation, and corrosion progression under actual operating and environmental conditions. These data streams feed directly into nonlinear finite element digital twins capable of capturing realistic structural behavior, including plasticity, buckling, progressive damage, and collapse mechanisms. By tightly coupling real-time data with physics-based simulation, DHE enables continuous estimation of remaining useful life, rather than relying on fixed design life assumptions. This allows engineers to clearly distinguish between benign aging and emerging structural risk. Structural healthcare, therefore, is not about identifying failure after it occurs. It is about understanding how close a structure is to its true safety limits and intervening early while safe, practical, and cost-effective options still exist. Digital healthcare engineering is equally transformative for machinery and energy systems, where unplanned failures are costly, disruptive, and potentially hazardous. Rather than relying on fixed calendar-based maintenance intervals, DHE enables condition-based and predictive maintenance driven by real operational data. Within a DHE framework, real-time sensors continuously monitor key parameters: vibration, temperature, pressure, efficiency, load, and wear across engines, generators, propulsion systems, energy storage, and power management systems. These data streams feed digital twins of machinery and energy systems, enabling early detection of deviations from healthy operating behavior. AI-enhanced diagnostics then move beyond simple threshold alarms. They enable fault diagnosis and prognosis, identifying not only that something is abnormal, but what is likely to fail, why it is failing, and when intervention is required. At the same time, digital twins support energy system optimization, balancing performance, fuel or power consumption, emissions, thermal limits, and component health under real operating conditions. Machinery and energy healthcare therefore transforms operations, from reactive repair and emergency response to intelligent planning and proactive intervention. The result is reduced downtime, improved safety, higher efficiency, and extended life of critical energy systems. Digital healthcare engineering does not stop at steel and machinery. It explicitly recognizes human well-being as a core element of system safety. In complex maritime operations, the health of the ship and the health of the crew are inseparable. Within a DHE framework, fatigue is monitored proactively, using a combination of work-rest patterns, operational schedules, wearable or onboard sensors, environmental conditions, and voyage context. This enables the early identification of excessive fatigue long before it manifests as human error or accidents. Beyond physical fatigue, DHE also addresses cognitive load. It recognizes when operators are overloaded by alarms, information flows, or decision pressure, particularly during abnormal operations, emergencies, or high-consequence situations. By integrating human state data with structural and machinery data, DHE supports safe manning strategies and intelligent operational planning. Workload, automation level, and human capability are continuously aligned rather than assumed to be constant. Crucially, this must be achieved with strict ethical safeguards. Transparency, data minimization, privacy protection, and informed trust are essential. Human data must be used to support people, not to monitor or penalize them. In the next century, caring for ships means caring for people, not as external operators, but as integral components of a living maritime system. When all the elements we have discussed come together, ships of the next century can no longer be viewed as static machines. They must be understood as living cyber-physical systems, continuously aware of their own condition, their operating environment, and their operational context. A living ship is self-aware. It continuously senses structural stresses, material degradation, machinery health, energy flows, environmental loads, and human performance. Through the integration of real-time sensing, digital twins, and AI, it is also self-diagnosing, interpreting what this information means for safety, reliability, and long-term integrity. A living ship is also continuously learning. As it operates, it refines its digital models, improves predictive accuracy, and adapts to new conditions and behaviors, rather than relying on assumptions frozen at the moment of delivery. Most importantly, these ships are designed for longevity. They are conceived to operate safely and efficiently for decades, with health awareness embedded from the outset, enabling informed life extension rather than premature obsolescence. This does not imply that ships become autonomous organisms. Rather, it signals a fundamental evolution in engineering, from building inert objects to sustaining living systems where awareness, learning, and care are central design objectives. In this paradigm, safety and sustainability are no longer enforced intermittently. They are continuously maintained as intrinsic properties of the system itself. Traditionally, ship design has focused on preventing failure. However, in a world characterized by uncertainty, extreme events, and long service lives, absolute failure-free operation is neither realistic nor achievable. The ships of the next century must therefore be designed to be failure-tolerant, capable of surviving, adapting, and recovering when things go wrong. Resilience can be understood through three essential capabilities. First, anticipation, recognizing emerging risks before they escalate, enabled by real-time monitoring, prediction, and situational awareness. Second, absorption, maintaining critical functions during extreme or abnormal conditions through robust structures, redundancy, and adaptive operation. Third, recovery, restoring functionality safely, efficiently, and decisively after damage or disruption. Digital healthcare engineering provides the enabling infrastructure for all three capabilities. By integrating continuous sensing, living digital twins, AI-driven intelligence, and secure data transmission, DHE allows ships to understand their own condition, respond intelligently under stress, and support informed decision-making during and after extreme events. Resilience thus becomes a deliberate design objective, not an accidental byproduct of conservative design. In the next century, maritime safety will be judged not only by how effectively ships avoid failure, but by how robustly they endure, adapt, and recover from it.
What is the essential differences between structural health monitoring and digital healthcare engineering? And why does this distinction matter for the next generation of the maritime systems?
Yeah, it is essential to distinguish between conventional structural health monitoring and the digital healthcare engineering framework. Conventional structural health monitoring primarily indicates when something is wrong. In contrast, digital healthcare engineering explains why it is wrong, what it means for safety and operation, and what actions should be taken next, while explicitly protecting human well-being. Digital healthcare engineering reframes monitoring as healthcare, a real-time, intelligent, life-cycle, predictive, human-centered, and resilience-oriented framework. This paradigm shift is particularly critical for SMR-powered ships, maritime autonomous surface ships, aging fleets, and other safety-critical maritime systems, where early diagnosis, informed intervention, and sustained operational integrity are essential.